Computer visions are transforming industries by allowing machines to interpret and make decisions based on visual data. Much like a human visions, by recognizing patterns in images, computer visions powers applications like medical imaging, autonomous driving, facial recognitions, and many more. Hi there, my name is Chris. I'm a data scientist specializing in AI and machine learning for healthcare with passions for innovations and impactful solutions. So thank you for stopping by and taking time to review and watch this video. So let's dive deeper into the concept of computer visions and CNN, Convolutional Neural Network. At the heart of deep learning are ANN, which stands for Artificial Neural Network, which is inspired by a human neuron that process data through connected layers of neuron. While effective in many tasks, tabular data tasks, ANN struggles with the image processing, particularly in maintaining septal relationship. For instance, ANN may not recognize rotated or shifted objects, limiting their effectiveness in a task that requires septal awareness. This is where CNN excels, as they can capture septal hierarchies within the images, which is critical for the task like object detections and classifications. As you can see in the example image of Batman under or above or between the cop beside the cops. Key advantage of CNN over ANN is translations variance, which is the ability to recognize patterns regardless of their position in image. So CNN achieves this by using a convolutional layer with filters that slides across the image. This approach allows CNN to consistently detect features like edges or textures regardless of the object locations. This property makes CNN powerful in applications where object locations may vary, and which it does most of the time, such as facial recognitions and object detection. CNN are optimized for grid-like data, like we mentioned, images through a layer approach. They automatically extract features from images, making them idle for tasks like image classifications, object detections, and also image generations. CNN architecture includes convolutional layers and pooling layers for feature extractions, followed by fully connected layer for classification. These structures allow CNN to excel in a diverse field, from diagnostic medical images to enabling autonomous driving by effectively learning complex visual representations. Understanding the CNN architecture is crucial for mastering deep learning in computer visions. The strategic flow begins with input data, typically an image matrix representing a raw visual information. Convolutional layer act as a features detector, identifying critical elements in the elements like edges, and activation functions adds non-linearity, enabling the network to learn from the complex pattern. Pooling layer reduces the subtle dimensions, focusing on the essential features of the images, and then flattening transforms features map into 1D vector for fully connected layers. And a fully connected layer combines learned features for classifications. Then softmax layer provides probabilistic output, computing the transformations from raw images to a classified result. So this structured approach makes CNN powerful for tasks like detecting cars, people, objects in the images and classifying them accurately, as you can see in the image. Convolutional layers are fundamental to CNN. By applying small weighted filters over the image, this layer extracts feature maps that capture essential visual elements such as edges and textures. Strides controls the movements of the filter, balancing detail and computational efficiency. So this process enables CNN to learn hierarchical representations of visual data, maintaining septal relationship and making CNN idle for tasks like requiring septal awareness, such as object recognitions. The convolutional operations consist of three main steps. First, multiply and sum. Filter values are multiplied with the corresponding pixel values. Second, feature map creations, summed result from feature map that highlights the key features. And third, dimensionality reductions. This reduces the image size while retaining all the essential information. Padding is crucial in CNNs, enhancing their ability to process image data effectively by adding pixels around border of the image input image. No padding leads to smaller outputs, potentially losing edges information, while some padding maintains the input dimensions, preserving septal relationship. Padding choices allows CNN to adapt to the specific task, balancing features, retentions, and computational efficiency. Pooling layers perform dimensionality reductions and dimensionality reductions, retaining all the key information while controlling overfitting and reducing computational load. They support CNN translations variants that we talked earlier, enabling the network to recognize objects regardless of their locations. Max pooling and average pooling are the two commonly used for summarizing features within local regions, supporting CNN's ability to build hierarchical visual representations and improving the robustness in image-based tasks. Digital images often have three channels represented as separate matrices, allowing CNNs to capture diverse features across color spectrum. Different features may be more prominent in one channel over the other. So by applying unique channel to each channel, by applying unique kernels, not channel, to each channels, CNN can analyze color-specific patterns and textures, enhancing the accuracy in tasks like object recognitions and also tasks like cancer cell image classifications correctly. Flattening transforms multidimensional feature maps into a single dimensional vector, preparing the data for fully connected layers. So this layer preserves all information while making it while making it suitable for traditional neural processing. Fully connected layers uses their vector to integrate features and classify the image, converting complex septal data into a clear classifications output. In healthcare, where I've mostly focused on, CNNs are invaluable for tasks like blood smear analysis, just to give you one example. The workflow starts with defining a use case, followed by a data preparations, data collections, pre-processing, strategic data splitting for robust training and evaluations. The iterative model buildings and optimizations ensures high accuracy. Deployment transitions the model to a productions, generating real-time insights while continuous maintenance ensures relevance over the time period. So this roadmap emphasizes creating scalable, adaptable solutions for evolving healthcare need in the field of computer vision and image analysis. While CNN are very powerful, they come with some challenges, as we all know. Overfitting can cause poor generalizations of new data, which can be addressed with the techniques like dropout, data augmentations, and many other. CNN requires significant computational resources, making efficient architecture design and resources management are crucial for scalability. Productions deployment also poses challenges such as latency and real-time demands, requiring optimizations and careful monitoring for consistent performance. Looking forward, I believe CNN and deep learning are set to evolve even more, expanding into a field like healthcare, finance, automobile, security, many more. Innovations like deeper networks and transfer learning continues to enhance CNN capabilities. As a data scientist and ML engineer leveraging CNNs in healthcare, my goal is to harness this technology's potential to solve real-world problem and create a meaningful impact, particularly in the diagnostic. So shown here is an example of medical image classifications, which highlights CNN potential to improve diagnostic accuracy and efficiency across various imaging and applications. Thank you all for taking time to listen to my presentations on CNN Convolutional Neural Network. I hope it gave you guys some valuable insights into how CNN works and their informative applications, especially in the field of healthcare. I appreciate your attention and curiosity, and I'm excited for the future discussions. Let's go.